7.3, page 4 and 5. My notes are very abbreviated. Mine are very dense here, so you might need to expand. I don't mind writing stuff up. That's why I'm putting this up. The theory is eigenvectors, and eigenvalues. They are used all over the place. Biology, a lot. Physics, engineering, a lot. In fact, and this really took, because of this theory, engineering really took off. Especially aeronautical and, what's the other one? Aerospace, thank you. Here is a matrix equation. AX equals Y. Right? AX equals B. AX equals Y. AX equals 0. Things we've been working with. I gave you on the quiz on Wednesday, AX equals X. And I answered for the bonus. And I said, what the determinant of what matrix do you care about? And it was the determinant of the matrix A minus I. Do you remember that? We talked about that yesterday. It was A minus I, that matrix, which actually comes into play. Well, what we're going to see with our differential equations, what we're going to see in a lot of situations in real life is, when is it that when I do a transformation, I have a vector and I do this matrix transformation. A matrix actually transforms space, like your Jacobian, as you learned, transforms space, you morph space. A matrix will do a linear transformation to a vector. As I change the vector, what vectors stay put? It's very important to ask, if I'm transforming a space, what doesn't change? This is usually known as the kernel, the space or the area that does not move. Okay? For instance, if I spun this whole room around this sign, I just spun it, this sign would not move, right? So a vector, let's say emanating from this, may not move if it's on the right axis, if I spun. Okay, those types of things. Again, computer programmers, you know how important this is. When you rotate your mouse from left, right, moving theta, how do you rotate your matrix? This is very important. So what vectors stay put or are just scalar multiples? Because as long as they don't change direction, if they stay parallel, if there's just a scalar of the vector, that's good enough. That's keeping it, at least with respect to rotation and translation, not moving. It may augment it, it may stretch it, space may be stretched, but you're going to find out how we can adjust for that. So what doesn't change? That's what this equation says. For a constant lambda. Now what was lambda before in multivariable? Do you guys remember what lambda was there? Lagrange multiplier. Good, good. This is known as the eigenvalue in linear algebra. The value that does not change. Questions on the understanding of this? Okay, do you agree that this equation is the same as this equation? Which is the same as we did for the bonus, this equation, which we've made homogeneous. That's what I have written on the paper. Lambda is not something that can keep changing. It's not like our alpha and beta, okay? Lambda is a specific value. For a specific lambda, there's things that happen here. Most of the time, there's a lot of lambda values where the determinant of this thing won't be 0. But what we care about, where the dependence occurs, is when the determinant of this thing is 0. And that can happen only for certain lambda values. So, as before, halfway down, as before, this is true if and only if the determinant is 0. Then it's a singular matrix. Then we have a limitation. So the determinant of this matrix is the key. We want this to be 0. What lambda values work? Well, let's hold on a second. Let's make sure we understand what I just wrote. Let's write a quick example. Let's make A a matrix. Somebody start yelling out numbers. I'll just write them. Let's write out 5, 17, 1, 9, 23, 42, pi, negative 71, E. Great. We've got a matrix. That's our matrix A. What would A minus lambda I look like? I has a 1 on the diagonals, agreed? So I'm going to put lambda times 1, or lambda on all the main diagonal. When I subtract the matrices, I'm going to subtract 0, really, from most positions, right? I's got zeros everywhere, except along the main diagonal. This matrix will be 5 minus lambda, 17, 1, 9, 23 minus lambda, 42, pi, negative 71, and E minus lambda. How we do it? Yeah. If I take the determinant of this matrix and I want to set it equal to 0, the determinant of this and set it equal to 0, what do I get? If I took the determinant of this right now, would I get a vector? What's the determinant give me? A number. Now, I've got variables in the locations, don't I? So what am I going to get? This equals a polynomial in terms of lambda. I get some polynomial. Maybe I'll get lambda squared plus, well, let's see, lambda cubed, right? I get a negative lambda cubed plus E times 23 minus, I don't know, whatever, 5 times 23 is 115 minus 5E times lambda squared plus, oh my gosh, I just have to do this big matrix, right? I have to do the determinant of this. I get a lambda term, and then I get a constant term, maybe, I don't know, favorite number 5, sure, whatever, equals 0. I get a polynomial in lambda. What does this allow me to do? Solve for lambda. By the fundamental theorem of algebra, we know that every polynomial has solutions. Where will the solutions most likely be and not be able? Imaginary. We're going to get complex numbers. How do complex numbers always show up when we solve a polynomial? Conjugate pairs. We're going to get conjugate eigenvalues. Conjugate eigenvalues. Real eigenvalues. Maybe we get repeated roots, repeated eigenvalues. We get specific numbers, though. Maybe lambda turns out to be 17. Like 17, whatever. Something, oh, we already have 17. It's my favorite number. 7. We'll have lambda equals 7. Lambda equals 2i. Lambda equals negative 2i. Maybe those are our 3 values. Clearly they're not because we have pi's and e's involved, but let's just theorize here. These are the coefficients then. These are numbers that for this specific matrix, A times x equals 7x. What vector x? What vectors does this work for? Every vector. Any vector x has this property. That's why it's important. Okay, so let's get into an example there. Let's just, this is one where you'll want to work it out. So I'd like you to maybe pull out some scrap paper, or is there a blank page anywhere on the back? On the back of page 5 at the bottom. Copy down example 4 there. The matrix, 3, negative 1, 4, negative 2. Just try this technique with the matrix 3, negative 1, 4, negative 2. Find the eigenvalues of this matrix. Find the eigenvalues of this matrix. Find the eigenvalues for this matrix. Find the eigenvalues for this matrix. Eigenvalues correspond to a what? Eigenvalues correspond to what? Eigenvalues correspond to a matrix. Not an equation, not a Diffie-Q, not a Wronskian. Eigenvalues go with a matrix. Eigenvalues matrix.